eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here, along with my younger brother, AJ Raj. Before I even get into what we're going to be discussing today, I do want to bring something up. One, you might see the recording studio is a bit different because we are not in our usual recording studio. This is going to be our temporary recording studio before we get back to the usual one. In addition, you'll also hopefully see on our YouTube channel that the previous video that came out was actually what we did as eCore as a community during the COVID-19 crisis. Just to quickly summarize, we as a community raised funds and donated medical supplies such as masks, gloves, ventilators, and cannulas to the government hospital in Namakkal, which is a district in South India. Along with that, we ran a food drive where we actually made homemade food and we packaged it for locals here who are not very fortunate, especially when the crisis with COVID-19 hit India very hard. So in order to support us, we would love it if you could go check out that video. It's really only 4 minutes long, and you can see everything we've done, everything that actually got published in the Indian Express, which is a national newspaper. So please go check that out before you watch this video. How about, what are we going to be discussing in this video? So this is an Algebra 2 video, as you can see, and in this video, we're going to be concluding our series on inverse relations and functions. So this is part 2 of inverse practice problems. We already did a part 1. You can find it in the playlist, and I would highly suggest you go check that out first. And even before you check that out, I would check out the 3 lessons I've made just so you understand what exactly inverse relations and functions are. So in this video specifically, we'll be doing 4 practice problems. These practice problems are going to include finding inverses, finding the domain and range, determining if an inverse is a function, 1 real-world application, and looking at composite functions. So in the first problem, we'll be looking at domain, range. Obviously, we're going to find the inverse first. Then we'll be looking at the domain and range of the function and its inverse. And then we'll be doing a function test to determine is the inverse actually a function as well. In the second problem, we're doing a real-world application that has to do with temperature conversions between Fahrenheit and Celsius. Fahrenheit's usually used in the United States, and Celsius is used more in like the eastern part of the world, such as Europe and Asia. And then in the third problem, we're going to be looking at composite functions involving a function and its inverse, a topic we've already gone over. And the last problem is going to be another finding an inverse and then determining if the inverse is also a function. So before we get into the video, I would really appreciate it if you could like, subscribe, hit the post notification bell, drop a comment down below, and share using all of our socials. Let's get right into the video. So we're going to start with our first practice problem, and the first practice problem is on domain, range, and then we're going to do a function test. So the problem itself is, for the function that we're going to be looking at, find the inverse first. So the function is, you can see at the bottom with a bullet next to it, f of x equals 2x squared plus 2. So we're going to find the inverse of this function. Then we're going to find the domain and range, so set of x values and y values that belong in this function and its inverse. Then after we do all that work, we're going to determine if the inverse of this function is also a function, meaning does it pass the vertical line test and is the domain continuous? So can we plug any input, any x value we want in the function, and when we get a viable output? So let's move on to the solution, which I actually put on a separate slide for the same problem. So here's your solution already pre-written. As you can see, the inverse is not going to be a function, and hopefully you noticed that because the original function we were given was a quadratic, which is pretty much a square function if you want to think of it that way. And when we find the inverse, we're pretty much doing the opposite operation. So the opposite of a quadratic is essentially a square root function. So a square root function, as we know, is not a true function because the domain is not continuous from negative infinity to positive infinity. Therefore, we should automatically know that this is not going to be a function, but obviously let's do the work and understand how we get to that conclusion. So I'm going to be running through this problem with you now. So I'm going to write the original function, which was f of x equals 2x squared. So the first thing we want to do is we want to find the inverse. To find the inverse, what I'm going to write this is, I'm going to write this in terms of x and y. So I'm going to replace the f of x with 2x squared. Y. And then I'm going to write the 2x squared on the other side of the equal sign. Afterwards, what we do is we switch the y and the x. So remember, that's our first step. So I'm going to rewrite this as x equals 2y squared plus 2. Now all we have to do is our last step, which is solve for y, and we'll find the inverse. To solve for y, we have to isolate y. To isolate y, we can first move 2 to the other side by subtracting 2. So we'll get x minus 2 is equal to 2y squared. Our next step is to divide both sides by 2 to get the y squared by itself. So then we'll end up getting, if I continue my work up here, x minus 2, we're dividing this whole expression that was on the left side of the equation. We're dividing that whole thing by 2, and what's left on the right side of the equation is y squared. Afterwards, what we're going to do is we're going to square root both sides of the equation. So if I do that, I'll get y is equal to, and I want you to keep this in mind, when we're square rooting something, especially a quadratic, we originally start with a quadratic. And a square root function only takes into consideration half of the curve. So therefore, we need to add that plus or minus sign in front of our square root sign. So we'll end up getting plus or minus the square root of whatever was originally on the left side. So that was x minus 2 over 2. We can rewrite this as an inverse function with inverse notation. So f to the power of negative 1 of x is equal to the positive or negative square root of x minus 2 over 2. So we found the inverse. That's probably the first part of this problem. Now we have to understand what the domain and range of both the function and its inverse are. So first, let's find the domain and range of the function f of x, which is 2x squared 2x squared plus 2. So f of x. What is the domain? Well, we can see that this is a quadratic, and as I've told you before, quadratics are polynomials, and polynomials have domains that are continuous from negative infinity to positive infinity. This is because all polynomials qualify as functions. They pass the vertical line test. I can pick any x value I want and input it into 2x squared plus 2, and I will get a y value. I will get an output. I won't get something that's undefined. Therefore, the domain is continuous from negative infinity to positive infinity. Eventually, when you get to pre-calculus and calculus, just by looking at a function, especially if you can see that this is a polynomial, which it is because it's a quadratic, you'll immediately be able to tell that this is a function. So we already know this is a function because we can input any x value we want. So therefore, we write that as an interval notation, parenthesis, negative infinity to positive infinity. As for the range is a bit more tricky because think of it this way. We're working with a parabola. So this is going to be y equals x squared. And what happens is y equals x squared is the parent parabola. Remember, it has its vertex at the origin. So what happens is if I draw this on a coordinate plane, this is what that parabola is going to look like. So the origin is the vertex right here. However, as you can see, we have a 2 infinity x squared. Don't really worry about that. That's the compression or stretch factor. But what we really want to focus on is this plus 2. So this plus 2 is pretty much going to shift the vertex up from the origin to the point 0, 2. So it's going to be shifted up plus 2 units. So if it's shifted up plus 2 units, if you look at this parabola doesn't even go into the third and fourth quadrants. Therefore, if this parabola is pushed up to the point 0, 2, what's going to happen is the range is going to be pushed up as well. So the range originally was from 0 to positive infinity, because we wouldn't have a negative range because when you square a number, you don't get a negative number. In this case, it's still going to be 0 to infinity, but we're bumping it up 2 because this parabola is translated up 2 units. So the new range is going to be 2 to infinity. Remember, the range doesn't have to be continuous from negative infinity to positive infinity in order to have a function. The domain has to be. So this still qualifies as a function. But however, the test we're doing is for the inverse. So f inverse of x. We're testing if this is actually a function. So the domain of f inverse of x. A really short way to think about it is we can take the domain and range of f of x and just swap them, because remember, the domain of f of x is technically the range of its inverse, and the range of f of x is the domain of its inverse. So we can literally just take the domain and range we found and then flop them. So the negative infinity to positive infinity would be the range. So negative infinity to positive infinity, and then the domain would be bracket 2, because remember, we're including the 2 to infinity. And even if you didn't know that, what you could do is you could take the inverse function, and you could take just the x minus 2, because that's the numerator. Set that equal to 0. Find out when this is equal to 0, and that's when x is equal to 2, because 2 minus 2 is equal to 0. And then you'll see that x has to be greater than or equal to 2. And why is that? Well, if x is equal to 2, 2 minus 2 is 0 in the numerator, and 0 divided by 2 is 0, which is okay, because 0 divided by a number is acceptable. However, when you square root that, you'll get 0, which is also acceptable. Just keep listening. However, if I decrease this to, let's say, 1, 1 minus 2 is going to be negative 1. Negative 1 divided by 2 is negative 1/2. And then you see we have to take the square root of that. We can't take the square root of a negative number. That's where you get this hyperbola, which is lying on its side. So where this vertex is going to be at the point 2, 0. So that's how we determine that the domain is not continuous. And if the domain is not continuous, then this is simply not a function. And that's pretty much it for this problem. So let's move on to the next problem. Problem number 2. This is going to be our real-world application. Here's the problem. I know it looks kind of long, but it really is pretty straightforward. So we're going to look at the formula for converting from Celsius to Fahrenheit, which are both ways to measure temperature, and the formula is F, which is Fahrenheit, equals 9/5 C, which is Celsius, plus 32. So this is the formula we're being given. This is the actual formula to calculate and to convert between Fahrenheit and Celsius. What we're being asked is to find the inverse of the formula and determine if it is a function. So we did something similar to this when we looked at the real-world application of the person diving off of the cliff. While we didn't find the exact inverse of the formula, we still solved a problem related to the inverse, but in this problem we're going to be finding what exactly is the inverse of the formula. And the reason we're finding the inverse of the formula is because we want to do the next step, which is use the inverse to find the Celsius temperature that corresponds to 25 degrees Fahrenheit. With the formula we've been given, we're assuming that someone's going to give us the input, which is going to be Celsius, and we're going to find Fahrenheit. However, we want to pretty much find the inverse to reverse that, so we can reverse our input and output. So instead of inputting Celsius and outputting Fahrenheit, we want to be able to input Fahrenheit and output Celsius. So that's why we're finding the inverse, which is pretty much the opposite, which will let us plug Fahrenheit in to get Celsius as the output. So here is our solution. As you can see, it's really not too long, and it's really not too complicated. So we're going to be walking through this together now. The first thing I want to do is write the original formula we've been given, which is Fahrenheit F is equal to 9/5 C plus 32. And what I want to do next is I want to write this in terms of x and y, as we do. Even if we're given f of x, we always rewrite it in terms of x and y. So in this case, f is going to be our y, and c is going to be our x. Because c, which is Celsius, is what we're inputting, which is x, and f, Fahrenheit, is what we're outputting, which is y. So y is equal to 9/5 x plus 32. So our next step is going to be switching the places of x and y. So I'm going to rewrite this as x is equal to 9/5 y plus 32. Now what we want to do is we want to solve for y, so we want to isolate y. Our first step is to subtract this 32 from both sides, so we'll get x minus 32 is equal to 9/5 y. Afterwards, I'm going to continue my work up here. We're going to multiply both sides by 5/9, which is the reciprocal of the fraction 9/5. If we do that, if we multiply both sides by 5/9, what happens is 9/5 times 5/9, which is a reciprocal, it's going to cancel out and give you 1. And that means that we have 1y, which is just y, which is what we want. We want to get y by itself. So we're going to multiply both sides by 5/9. And if we do that, if we multiply x minus 32 by 5/9, then we're multiplying the numerator by 5, because 5/9, 5 is in the numerator. So 5 times x is going to give us 5x. And 5 times negative 32, 5 times 32, if you do the math, you'll end up getting 160. So you're going to get minus 160, and because we multiplied by the fraction 5/9, the 9 is going to go in the denominator because it wasn't multiplied with anything. So the 9 is going to go in the denominator. Our next step is we want to pull the 5/9 back out of this. What do I mean by that? Well, we want to divide this whole fraction by 5/9. If we pull 5 out of the numerator, we're going to end up getting x minus 32. If we pull 9 out of the denominator, we're going to get 1. So we'll end up getting 5/9 times x minus 32, which is exactly what we were originally doing. So this is pretty much our finished formula, finished inverse. And what we're going to do now is we're going to write this in terms of Celsius. So y has now become C, which is Celsius, and x has now become F, which is Fahrenheit. So this would become C equals 5/9 F minus 32. And we were asked, is this a function? Well, it is a function. Is a function. Because as you see, if we multiply this out, there's a constant in the denominator. If there was maybe an x or a variable in the denominator, then this would not be a continuous function. The domain would not be continuous because there would be a value. For example, if we had 9x in the denominator, if we plug 0 in for x, then this function would be undefined because you cannot have a numerator that's a number divided by 0, which is the denominator. However, just because we just have a constant in the denominator, so we can pretty much rewrite this fraction as 5/9 x minus 160 divided by 9. And you can simplify that as you will. And this is, as you can see, a linear function, and that it counts as a function. A line passes the vertical line test, and it has a continuous domain. So this is a function. The next part of the problem that we should quickly do is our input. We're being given Fahrenheit is 25 degrees. So we were trying to find Celsius. So let's use the formula we found. So C equals 5/9 times, we're going to input 25 for F, because that was what we were given in the problem on the last slide. We're just going to simply solve this. So we're going to end up getting 5/9 times 25 minus 32, which is -7. If we multiply this, we're going to end up getting about -3.9 degrees Celsius. If you put it in a calculator, I think you'll get like 3.8888, and we can just round it to the nearest tenth, and this is the answer we get. So this is the solution to this problem. So if we move on to the next problem, you can see problem number 3 is composite functions and inverses. I quickly just want to cover, we talked about composite functions, which in simple terms is just a function within a function. And you'll see that little circle, and that also stands as a function, as a composite function operator. So that pretty much tells you this function is within this function. Whichever function on the inside is what you do first, and whatever function on the outside is what you do second. You'll usually be given what the function is, and then you'll be given this in function notation, either with a function operator or sets of parentheses, and then you'll be given an x value, which you'll input into the first function and then the second function, and I don't know, maybe you'll have more functions outside, but for our purposes, we'll be working with 2 functions in a composite function. In this case, the 2 functions we'll be working with are the original function and the inverse. What holds true for functions and inverses is that if the number we're inputting into both the function and the inverse, so whatever number we're given, the x value, if that number belongs in both the domain of the function and the inverse, meaning even if they're not true functions, as long as this value we're inputting belongs in the domain, meaning the answer is not going to be undefined, we'll get some tangible real answer for y, for our output, that means that whatever we originally input is going to come right back out. Because if you think about it, whatever we input, the first function is going to, you can think of it like messing it up. So let's say we input 5 into our composite function consisting of function and inverse. So if we input it, the first function, whether it be the function or the inverse, is going to mess it up. And then after that, we're going to input into the next function, which is on the outside, and that's going to undo what was done, because functions and their inverses are pretty much opposites. So what our operations you do with the first function, the second function is going to undo. That's pretty much what we're trying to demonstrate in this problem. So let's get into the problem. So we're going to find the value below given f of x is equal to 10x minus 10. So we're given what the function is, 10x minus 10. Then we're told that the composite function is, we're trying to find f inverse of f of 10. So first thing we have to do, which is not blatantly explained, is we need to find the inverse given f of x. After we find the inverse, we're plugging 10 into f first, because that is the function in this notation that's closer to 10. We're going to plug 10 into f of x first. Then we're going to plug whatever value we get from that into the inverse, f inverse. So here's your solution pre-written, and I'm going to be running through that again with you. So the first thing I'm going to do is I'm going to write what the function we've been given is. So the function we've been given is f of x is equal to 10x minus 10. I'm going to write this in terms of x and y as we usually do. So y equals 10x minus 10. And now what we're going to do is we're going to swap x and y. So we're going to write this as x equals 10y minus 10. Now we're going to solve for y, trying to isolate it. So we're going to first add 10 to both sides, so we get x plus 10 is equal to 10y. And then all we have to do now to get y by itself is divide both sides by y. And we get 10. And if we do that, we get y is equal to x plus 10 divided by 10. And we can leave this as is. And if you want to write this in proper inverse notation, it says f to the power of -1, f inverse of x, is equal to x plus 10 over 10. All right, so we found the inverse. Now what do we have to do? Well, we have to put it into this composite function. So the composite function we've been given is f inverse of, so function operator of f of 10. So let's write this in terms that are better for us, which is the parenthetical terms that I usually use. So f inverse is on the outside of f of 10. So that's how we're going to solve. So since f is closest to 10, that's the function we're going to apply first. So f of 10, well, f of x is equal to 10x minus 10. We're plugging 10 in for x, so we're going to end up getting 10 times 10 minus 10. 10 times 10 is 100. We do multiplication first from PEMDAS, minus 10, and 100 minus 10 is equal to 90. If this holds true, if 90 belongs in the domain of f inverse, what's going to happen is we're going to get the original input, which was 10. So let's try that out now. So if we plug 90 into f inverse for x, so f inverse is equal to f inverse of x is equal to x plus 10 divided by 10. F inverse of 90 is going to be plugging 90 in for x, so 90 plus 10 over 10 is going to give us 100 over 10, and then look at that, our final answer is 10. So this worked out exactly how we wanted it to, and as you can see, 10, which we originally plugged into f of x, belongs in the domain of f of x, because 10x minus 10, which is f of x, is a linear function. It is a function, passes the vertical line test, and has a domain that goes from negative infinity to positive infinity. So 10 belongs in that range. So it belongs in the domain of f of x. Then the output we got, which was 90, also belongs in the domain of f inverse, which it was plugged into. If you look at f inverse, it's x plus 10 divided by 10, which can also be written as 1/10 plus 1. 1/10 x plus 1. And that is also a linear function. Linear functions, again, have pass the vertical line test and have a domain continuing from negative infinity to positive infinity. Because these two numbers belong in the domains of both the inverse and the function, we got the original value plugged in right back out with the composite function. And then moving on to the last problem, we're going to be finding an inverse and then simply determining, is this inverse a function? So it's pretty much a good recap of this whole mini series of lessons we've been doing. So here's your problem. Find the inverse of the function that's been given, which is f of x equals 2x squared divided by 5 plus 1, and determine if the inverse is also a function. So let's look at the solution. First, you can see we find what is the inverse, and then we determine, looking at just considering what the equation is, we determine is this a function or not. And I want you to notice again that the original function we're working with is a quadratic, and the opposite of a quadratic is a square root. And as we said, square roots are not true functions, so you can see the final answer is not a function. So let's run through this problem together. So I'm going to write the original function, so this is f of x equals 2x squared over 5 plus 1. What we want to do is write this in terms of x and y, so replace the f of x with y. We get y equals 2x squared divided by 5 plus 1. Now we're going to swap the places of x and y, so we're going to rewrite this as x equals 2y squared over 5 plus 1. I'm going to continue my work over here. And now we're just going to solve for y, trying to get it by itself. So we'll subtract 1 from both sides first. So we've got x minus 1 equals 2y squared over 5. And then all we have to do is just multiply by the reciprocal, because we have a fraction here. Our fraction is 2/5. This is pretty much, so y squared is in the numerator, but if we separate this is pretty much 2/5 times y squared. And the reciprocal of 2/5 is 5 over 2. So we'll multiply both sides by 5 over 2 to get 1y squared, which is just y squared. So if we multiply both sides by 5 over 2, we're multiplying x minus 1 times 5, because that's the numerator of the reciprocal. So we'll end up getting 5x minus 5, and because we're multiplying 5 over 2, 2 is going to be in the denominator by itself, and we'll get y squared by itself. And the final thing we have to do is just square root both sides to get y by itself. So square root of y squared is just y, and then if we square the other side, we have to consider both the positive and negative square root, because our original function was a quadratic, and we need the complete curve of the square root. So we need a hyperbola, not just a curve of one side of the square root. This is going to be our final answer, and then we can rewrite this in proper inverse notation as f inverse of positive or negative square root of 5x minus 5 over 2. And you can simply see that this is not a function, because as we said, square roots are not functions. because they don't pass the vertical line test because they're on their side like this, and they don't continue from negative infinity to positive infinity in regards to their domain. They stop here, and then you have all this extra space on the x-axis left. So if I do the vertical line test, we don't even have a value there. So the vertical line test is failed. And in addition to that, the domain is just not continuous, so I can't just plug in a value that does not belong in the domain. Let's say the vertex of this hyperbola is at like 2, 0, and then there's nothing of the hyperbola to the left side of this point. I can't plug in the point, for example, x equals 1, and then expect to get a valid output from the function. We're going to get probably undefined or unreal, something like that. So that was our last problem, and I hope you enjoyed the video. If you did, please like, subscribe, hit the post notification bell, drop a comment down below, and share using our socials. Also, check out our website and our Gmail for more information. And again, please check out that featured video on what we did during COVID-19. Your support is so appreciated. And if you support us, we can do more events like that where we help our community, not just ours, but all of ours out in whatever way we possibly can. Again, thank you for watching, and look for my next Algebra 2 lesson where we'll be starting a new topic. Thank you.